Hello. Hello. Can you hear me?
Yes, sir. We can hear you.
Okay, good. So, yeah. So before I start, so do you guys have any questions of on whatever has been done so far? Have you guys gone over the stuff that has been gone over so far? At least in the last class, the dynamic programming thing. Hello.
Yes, sir.
Yeah. So you have no questions, right?
I have one question in general.
Yeah.
So, like, see, the moment we started this graph algorithms, so we did not bother about checking for the like lower bound for each problem.
Yeah, we have not gone over the lower bound for each problem, and the reason is that we don't have any good lower bound.
But like in general, are these all search algorithms over some certain pattern? Say,
They are. I mean, you can think of them as search algorithms, but they're not search algorithms in some very ordered thing.
I mean, like we can search over a permutation tree or like general like functions from n like n numbers to n numbers.
Yeah, I mean, see, I mean, again, I mean, so they are search algorithms. Okay, I mean, what are searching? For example, if I am looking for the shortest path, right?
Yeah.
I mean, first of all, it's not exactly search algorithm because they are not decision algorithms. It's not like, okay, find a place or something. You're trying to optimize something.
Yes, yes.
Okay, but still you can call this one as a search algorithm that you are searching for the shortest path, kind of stuff like that. So among the set of paths, you are looking for the one which has the shortest path, right?
Yes.
So basically that is what you are doing, and then you can so call them as some kind of a search algorithm. Okay, so that is all fine, but again, I mean, just because we have some, they can be written as some search algorithm doesn't mean that we have some non-trivial lower bound. So for example, that in the case of the finding the shortest path, right? Now this is something that you can always say that, okay, I mean, maybe the shortest path algorithm must look at the whole graph. If some edges are not looked at, then possibly you'll be able to miss something, right? So there, any algorithm, any correct algorithm, has to run in times omega of size of the number of edges, size of v plus e. But that's about it. We don't have anything that says that we need or we can do it in that stage. And the best algorithm that we have is a v log v or e log v kind of stuff. So why is that extra log required? These are very, very important fundamental questions that have been open for quite some time. For BFS and DFS, it doesn't matter because BFS and DFS, the time complexity was already linear, right? So if an algorithm is linear, it means that it is looking at all, I mean, just to read the whole input, you need linear number of time complexity. So that's fine. So it is an optimal algorithm. But once something is not linear, for example, the shortest path, the Dijkstra's algorithm or Bellman-Ford and so on and so forth, they're not linear algorithms. The question automatically becomes that can you give me a non-trivial lower bound better than linear? And the basic thing is that no, I mean, we don't have any non-trivial lower bound. And this is so although whatever we are presenting now in this class, it can seem like that, oh, these are like the obvious algorithms and they are like have been well studied, all these problems and so on. But if you look at the most recent papers in, say, in graph theory or graph algorithms and all, every now and then you have some papers or other on this set of work. And any work on like this ST connectivity or ST shortest path sorry, I'm not ST connectivity, on ST shortest path and so on, they create some huge, waves in the community. Oh wow, why we have come up with a new algorithm? It is better than the previous one. Maybe for very special cases, but still it is better than the previous one, and so on. So the reason we are not talking about lower bounds here is because we don't have lower bounds, and it's something that we had kind of talked about in the beginning. That the lower bound techniques are not that easy, okay, and we have very few amount of lower bounds. I mean, we'll talk a little bit more about this lower bounds and the shortage of that or lack of it in the last section of our this course, in last 2-3 lectures. But yeah, if you have noticed that there is no lower bound, it's a very nice and interesting point that yes, we don't have any lower bound. We have not talked about any lower bound because we don't have any lower bound. Yeah, does it answer your question to some level?
Yes, sir.
Okay, so what about the rest of you? Any questions about whatever was done so far? So we basically were looking at the shortest path, single source shortest path algorithm, right? And so that's what we will be continue doing so today. But today's lecture will be possibly a bit short for one reason that I have to go a bit early. But that's fine. Let's start with them. So if you guys don't have any particular questions, so let me talk about the next chapter in the shortest path kind of stuff. So let's start with whatever we have, right? So we had this set of edges, so a graph with edge weights, and the length of a path is the sum of the weights in the graph. And the shortest path between any two vertex u and v is the length of the shortest path from u to v. And the weights can be negative also. And negative cycles is always a problematic thing. So we can assume that the graph does not have a negative cycle. Right? So this is something that we have been doing from before the mid-sem and even last class. And what we were doing till now is what is called the single source shortest path problem. So basically, you have been given a graph with possibly negative weights, but no negative cycles. And the goal is to find a shortest path between u to v. Or maybe one can say the shortest path from u to any other vertex. Right? Hello? Any questions? Okay. So this is something that we have seen so far. Right? Now let me ask a slightly more thing. What happens if you ask what is called all pair shortest path problem? The difference is kind of very minimal. Basically, you have been given a graph. Again, the edge weights can be negative, but there is no negative cycles. And your job is to find the shortest path between u to v for all uv pairs. Okay. Now you might say that, okay, how does it, I mean, how is it any non-trivial, right? Let's see what all things can be, we know about it. Maybe, do we have any algorithm for this all pair shortest path? Let me ask. Kaushik Pate, are you there? Kaushik Pate? Okay, not there possibly. Nirupam, are you there?
Yes, sir.
Do you know of any algorithm that will give us all pair shortest path problem? Hello. Sorry.
Bellman-Ford.
Bellman-Ford. How?
We are calculating
Bellman-Ford gives a single
shortest
source
path
shortest path.
between.
Bellman-Ford computes single source shortest path, right? All the shortest path from you to something else. Now, how do you?
Breaks down all non-vertices.
Right, exactly. So you can start any single source shortest path problem and run it on all the vertices, right? You get that all pair shortest path problem. So let's see what all things do we have now. So we can have the Dijkstra's algorithm. Dijkstra's algorithm was giving us O of V square algorithm. So if I run it on every vertex, so all pair shortest path will give me O of V cube algorithm. But of course, the problem is that it will give us only for positive edge weights. And for negative edge weights, we can use the Bellman-Ford algorithm again in the same way by applying the Bellman-Ford algorithm in all vertices or all vertices. And Bellman-Ford takes order of V cube algorithm, V cube step. Again, since we are running it over all possible vertices, so it takes order V to the power 4 steps. Okay. But the question is that can you do better? Okay. Now, so in this class, we will be looking at two such algorithms where we can do better. And the main idea will not be just to look at these algorithms as such, but to understand why or how is it that we are gaining from this whole thing. And the main idea will be actually for both of these algorithms will be kind of similar to Bellman-Ford, which is basically that we will be using something like a dynamic programming technique, right? So what is a dynamic programming? Okay, just let's quickly go over it. So dynamic programming is nothing but a kind of a recursive algorithm, right? Where you take the big problem, break it down into smaller problems. Now, in a recursive algorithm, if the smaller problems are being computed again and again via different branch of the computation, then the simple idea is to solve these subproblems and store the answers so that we can reuse those answers as and when required. Okay, and then combining those solutions, we can answer the subproblems. And the main trick of dynamic programming is to kind of think about how to break this algorithm into smaller parts. Let me ask somebody else here. Pallavi Datta, are you there?
Yes, sir.
Can you just recollect what was the kind of, how did you break this main problem into smaller problems in Bellman-Ford?
Sir, like in Bellman-Ford, we were finding the smallest path from say S to T, between vertex S to T. So we were like T was a destination vertex. So we were considering those edges or those vertices that were immediate neighbor of T, like U, V, W say. And we were calculating the shortest path from S to U, then S to V, then S to W. Now and we were also storing these results somewhere, because it might happen that these calculations might be later on required at some other steps, so that we don't have to redo all the work again. So after getting the shortest path from that S to U, V and W, we were just adding up the edge weights of UT, VT and WT, and then among them we were picking up the shortest length path.
Excellent. Yeah, perfect. So this is exactly what we are doing for Bellman-Ford. We were going down one step by one step. So if we were kind of reducing the path length, shortest path length from S to T, from N to N minus 1, and so on and so forth, right? Now, that is one way of breaking that problem, but that is by no means the only way. So let me present you one such very cute way of breaking this problem. Okay, maybe I can just use this my thing here. Okay, So, okay, just 1 second. Let me just quickly go over here. So let us define this following thing. So let DLUV be the shortest path of length, the length of the shortest path from U to V that uses at most 2 to the power L edges. Okay, 2 to the power L edges. Now, our goal is to define what? DL plus 1 UV. So what is DL plus 1? What is DL? So this is the shortest path, shortest length of paths with 2 to the power L edges. DL, shortest length, I mean here I am talking about DL UV, okay? So this is the, and DL plus 1 UV is what? The shortest length of path.
Yes, sir.
Yeah.
Are you writing something?
Oh, sorry. Somehow, why has this sharing stopped? I don't know what happened. Oh, sorry. I think you know what is going on. Do you see my screen?
Yes, sir.
Okay, sorry. So DL UV is the shortest length of the path with 2 to the power L edges, right? And DL plus 1 is the shortest length of path with 2 to the power L plus 1 edges. Now, what is 2 to the power L plus 1? It is 2 into 2 to the power L plus 1. 2 to the power L, right? Now, let's think about it. Here is U, here is V. Say, let's say I am looking at all the paths of length 256. Okay, of less than or equal to 256 with less than or at most, right? So this path is the shortest path of length at most 256. So think about somewhere in the middle. There is a vertex called T. What is the length of this path? Can somebody say what is the length of this path? Or how many edges are there in this path?
128.
Of course, it is less than 128, right?
Hmm.
And similarly here, this one has less than 128. So in this path, consider this half of this path, okay? How did we get this path? So this path should be the shortest path of length, also shortest path with less than or equal to 128 edges between U to T, right? So this path must be the shortest length of path from U to T with less than or equal to 128 edges. And similarly, this other part, maybe a different color, the purple. So this path will be again the same thing, right? Shortest path of length, shortest length of path from T to V using less than or equal to 128 edges. So see, that means I was looking at the shortest path of length at most 256 from U to V, but that I can get by trying to look at what DL UT and DL TV, right?
Sir, here length of a path doesn't include the weights. It's only number of
It is number of
edges.
edges, number of edges. Yeah, so shortest length, when I say shortest length, this means the weight. Sorry. When I mean length, it means the, so the length means sum of the weights. Okay, so that's why the shortest length of the path with less than or equal to 2 to the power L minus L plus 1 edges. That means, say for example, in this diagram, look at all the paths that has 256 less than or equal to 256 edges. Among those edges, among those paths, consider the path with the shortest weight.
Sir, but then there can be a single path from U to V with the shortest weight.
Yes.
In that case, we cannot break it into, like, there will not be any T in between.
I mean, there will not be T in between because the path itself, right? I mean, still it will be an D in between. Either there is an edge, completely an edge, right? Directly an edge, or there is something in between. There's some vertex, some edge in between, right? Vertex in between. So that vertex will give you the breaking point. So
Yes,
take, yeah.
but if the shortest length path is a single edge, then
Then it
T
is
will
not. I agree. If the shortest length pass a single edge, then no. Right? But for every other case, you can break it up into two smaller cases.
But for every other case also, how can we say that U to T is 128? Because
Not
less
120,
than
less than.
Okay, sir.
Less than or equal to 120. That's all I'm saying.
Sir,
Yeah.
like what will be D256 U to T? It will be the same path, right? Because
D256 U to T is
yeah,
basically the consider all the paths of from U to V that uses 250 less than or equal to 256 edges. Okay. Among all those paths, take the shortest. Okay, this is what we want to find.
no, like suppose that D U to V, like we found that somehow the shortest path of length less than or equal to 256.
Yeah.
Then like if T is a middle vertex,
Yeah.
then D 256 of U to T has to be the same path, right? Like if not,
That's true.
256 U to V has been
No, not necessarily. Maybe there is another path. Maybe there is another path which takes a much longer route to T, but that's a shorter path. But the shorter way.
less than or equal to 256. Okay.
Yeah, but there
Okay.
might be a path which uses more length, more
Okay.
number of edges, but the sum of the weights must be lower.
Okay. Huh, but I'm considering less than or equal to 256, right? Okay.
See, less than equal to 256 number of
Edges.
edges,
Yeah.
and the shortest thing is the shortest weight.
Thanks.
Luna, is your confusion sorted out, or
Yes, sir. Yes, sir.
okay? So basically, I mean, take any path which has more than one edge. Okay, you can take this middle vertex or close to the middle vertex. It's kind of the path which was at most 256, splits up into two edges of length 128 each, or less than or equal to 120. And they will basically give you the shortest path from U to T of length at 250. So therefore, what we can say, therefore, what can we say? So we can say that dl plus 1 uv is nothing but take the minimum over all the vertices t, okay, dl uv plus dl vu. Sorry, not vu, what am
Sir, UT.
plus dl, first of all, this is not uv, this is ut, and this is tv. Okay, and of course there is can be a path which is that, okay, I don't want to split it, right? As Luna was pointing out, that maybe I want to just live with the previous path, I don't want to add more edges. So that means and minimum of dl uv, right? So take the shortest path between u to v using less than 2 to the power l edges, or using 2 to the power l edges, go from u to somewhere else, and then from that place take another 2 to the power l edges and go to u v. And if you can do that, then you get the shortest path, the shorter of them. Okay, and this is the main idea about this particular breaking up into small problems. So if you go here, see here, and okay, now what happens with the one edge thing, that I kind of skipped. The one edge thing basically becomes the base case. Okay, so what is the shortest path between u and v that uses one edge? Of course, I know what is that. That if there exists a path from u to v, then shortest path is the weight of the edge uv, and else it is not possible to reach from u to v in one edge. So 0 means 2 to the power 0 is 1, less than or equal to 1 edge, right? And you have this. Actually, I mean, there's a reason why the other one, that dl uv, has not been written, or dl minus 1 uv, but that you can, I mean, if you want, you can still add this one, minimum of this quantity. So dl minus 1 u to w plus dl minus 1 w to v. And you can also take a minimum with dl minus 1 uv. Okay.
Sir,
Yeah.
sir, that 120, first we took the entire path as 256 edges, right?
Right.
So, but the algorithm that is saying that we have to check whether that is L lesser equals, sorry, that that should be lesser equals to 2 to the power L. So if I understand it correctly, then it should be 8, right? Instead of
yes, L is
256.
8. L is 8. Yes. So 256, this should be, sorry, you are right, completely right. So it should be, yeah, I mean, like whatever is written, right? So this 256 is 2 to the power 8, right? So basically what I have explained here is that d8 uv equals to minimum of, yeah, d7 ut plus d7 tv. This is what I just explained here using 256 and 128. Okay. But in general, this is the thing. Is it clear?
Sir, that half, like 256 length that we divided, and try to find the middle point and try to check the shortest path between u to t and then t T to V. But in this case, the L is equals to now 8. So now this U to T, this will become 4.
I didn't go from L plus 1 to L. From 2 to the power L plus 1 to 2 to the power L. So that's why I had written this one. 2 to the power L plus 1 is nothing but 2 into L, 2 to the power L. Okay. So that's why we are not going from, we are going from 256 to 128, or you can think of it that I'm going from DL plus 1 to DL, which means that I'm going from 2 to the power TL plus 1 to 2 to the power L. Okay.
Okay.
Yeah, good. So that is okay. Now, so since this W is taken over all V, so if you take W to be equals to V, then this is nothing but DL minus 1 UV, right? And that's why that extra minimum that I told is not required. Basically, this is already taking a minimum with this. So this is basically the algorithm that we can think of. So this is an algorithm. Okay. So let's see what happens here. So here is the graph, say, and I want to solve the all pair shortest path problem. So first of all, I have written dash for all these diagonals, which basically means that I'm not, I mean, the distance between A to B, B to B is all of them are 0 kind of stuff. So you can think of them as 0. Dash is a 0. And for now, I'll start with everything being infinity. Empty space means infinite, minus infinity. Okay. Okay. So now, what is the distance? Okay. So this is the starting case, right? So this is the D0. So all that I have done is that represented all the edges over here. So for example, A to B, the shortest path is -7, this one, right? And this is -7. So this is a good example actually, by the way, because when I was trying to find out whether I have made a mistake in the calculations and all those kind of stuff, I actually was not being able to, I mean, humanly, it took me quite some time to understand the minimum path from G to B. For example, can you find out what, can somebody tell me what is the minimum path from G to B?
So from
You got 6. G to F, F to E, E to
Yeah.
D, D to A to B.
Yeah, see, it's quite a convoluted path, right? G to F, F to E, E to D, D to A, and A to B, right? Now that thing will come out here. Okay, so let's see how. Okay. So in D0, I have basically added these edges. Yeah, by the way, somebody was asking some other question. Hello. Somebody was
sir,
asking, yeah.
I was just asking about the vertices that you asked. I heard that about, I guess you said D to B. I was not, I didn't clearly hear G to B.
Okay. Yeah. So now next thing that I want to do D1. Okay. Now see, again, I have to go over all the possible squares in that vertex, right? So for example, say if I want to compute the E to A, say E to A. Now E to A currently is basically infinite. It cannot go, right? Fine. But what we can go is that I can go to E to somewhere else. So E to say maybe B and B to A. Oh no, there's nothing like that. Sorry. Then E to C and C to A. Okay, nothing, no good. E to D and D to A. Oh yeah, so that is one possibility. So that means E to D is 10, D to A is E to D is 5, D to A is 5. So this becomes, so I can go from E to D in using this kind of step, using twice of this kind of stuff in 10 steps. Okay, and similarly I can do for all the possible pairs here. And by doing so, what happens is that you will see that I will be able to fill up this table, and this will be D1. Note that this will be basically the set of all. So among all the paths of length 2 or less, what is the shortest way I can go from a part 1 vertex to another? And this is what is written. Okay. Now the next thing will be, so for example here, like G to B, that was our current thing, right? Now G to B currently has 16, and basically it is G to, we got it from the previous one by saying G to E and E to B, 7. So 9 plus 7 is 16. So this. So now if I go to D2, what will happen? Right? So I can to look at, I can go to G to B directly. Just 1 second. G to B, right? Or I can go to G to C and C to B. Okay, so that is 10 plus 6, 8 is 18. Currently it is 16, so not good. See, by the way, G to C, when I'm saying, right, I have already said G to C. This matrix says that I can go from G to C, but that doesn't mean that I can go to G to C in 1 step. I can go to G to C in 2 steps, right? Because this is the matrix for D1. And similarly, we can talk about G to E. Okay, G to E is 3 steps, and E to B is 7. Okay, so E to B I can go in 7 steps. Okay, so 10. Oh, excellent. So I can now go to, therefore, G to B in 10 steps. So this 16 must become 10 in the next round, right? And see what happened there. G to E was done by G to E, so direct movement was there. Oh, sorry, G to E was 3, sorry, 3. So not direct movement. So G to E was going via G, F, E, and E to B was 7, which was the direct movement. So that gives us the length, path length 3, which is basically less than 4. And this is what came out. And now I go for D3. D3 means all the path length of less than or equal to 8. Okay. And less than or equal to 8. So one thing may be that, okay, how do I do it? I don't need to, I can look at this matrix and go talk about it. And if you see, what will happen is that we can say that, okay, G to E, I can go in 3 steps, and E to B, now I can go in 3 steps. Now you can say, how did I E to B suddenly become 3 steps? Because in the previous round, E to B, okay, went through 3 steps by saying that, okay, I can go from E to A in 10 steps and A to B in 7 steps. And A to A was basically a 2-step process. So 10 plus 7 is 3. 3 is less than 7, and that's what why this first updated to 3. So by doing so, I have gone from E to B, now has become 3, and in the next step, when I do D3, this will be updated to 6. Now note that I can stop here right now. Why can I stop here right now? Because at this point, I'm looking at all the paths of length 2 to the power 3, namely 8 paths, 8 length paths, paths of number of edges 8. And in this graph, there are only 7 vertices. So therefore, 7 is less than 8, and therefore we can stop here now. Okay, and this is basically the algorithm that you have. And the algorithm is basically simple. It's basically the repeated squaring kind of argument. If you do it with the weights 1, all the weights are 1. It is basically you keep on repeatedly square the adjacency matrix, and you check that after how many steps can I go into, how can I reach from A to A to B, okay, or U to V. Now, and that would give you the repeated squaring. So I run this one from 1 to log V number of steps. 1 to log V number of steps, and for all pair, I define it like this. Okay. Okay. So I have to go from 1 to log V number of times, and I do this whole thing. So note that for every time I have to fill up this whole square. Square is of size V square, and for each square I have to do a minimum over all the possible V's, right? So for every piece of the square takes V steps, there are V square number of a point whatever entries in that square. So every time I produce a new from DL, I produce a DL plus 1, it takes me V square number of V cube number of steps, and I have to do it log V number of times. So therefore the total complexity. Okay, so here the correctness algorithm, I'm not going to go over it, but this is exactly what we kind of described there. And the runtime is V cube log V. So is this algorithm kind of clear? So the algorithms and all are mostly easy, okay? None of them are hard. But the main idea or the beautiful idea is the first step. When you define DL UV, and you can define DL plus 1 UV using DL of some UT or something, so on. Any questions? Hello.
Sir, why it is V cube? The table.
Yeah, why is it V cube? Say, look at this table, right? How big is the table?
V square.
V square. How much time does it take to write this entry? So write this entry is basically I have to use this one, right? I have to look at for all W in V. I have to compute this one and take the minimum.
Okay.
Right? So for any entry in a table, I will have to spend V times.
Okay.
Okay, so every one, so for D3 to produce D3 from D2, I take V cube number of time. Okay, where V is for each of the entries. Okay.
Yes, sir.
Any other questions, doubts?
Sir, why you are considering 2 power error?
Think about it. Why am I considering 2 power n? See, again, these are the kind of questions that you should ask yourself. Okay.
Because of breaking it down, right? Every time.
Because if I don't consider 2 power n, then see the reason I am talking about log V is because of this 2 power n. I go from length 2, then length 4, then length 8, then length 16, and so on. So I have to just run it log V number of times. Note that in Bellman-Ford, this exact thing was done V amount of time. And that is also the reason why Bellman-Ford was taking such a long time. Okay, Bellman-Ford was going one by one. Here it is kind of splitting it into 2 halves. And that's the kind of trick about the whole thing. Okay.
Yes, sir.
Okay, so if this is clear, so what do we have here? So we had this Dijkstra's algorithm was giving us V cube, but it has only positive algorithm, positive weights. With Bellman-Ford, I could do it with V to the power 4. And with negative weights, with repeated squaring, I can go V cube log V. Now question is that can you do even better? The answer is actually yes. And again, let me just write down what the idea about the dynamic programming is. It is the last line that has all this thing. How you break a problem into smaller sub-problems has controls all the trick of it. Okay, so how are you defining what is it that we are computing? And that is something that nobody can teach you. It's a kind of a, it's a both of a practice as well as an insight, as well as your intuition, your creativity, your cleverness, and that is what gives you all those things. So for example, look here, okay? So now I have the vertices. So let's call the vertices a number, V1 to Vn. It doesn't matter how I number them. I number them somewhere. And I now define d of L of uv is the length of the shortest distance. I am not looking at the number of vertices, number of edges or something. I mean the length of the shortest distance from u to v, where I am allowed in the middle between u to v only vertices from v1 to vl, nothing else. So in some sense, I am not allowed to pass by any other vertex other than v1 to vl. Okay. Fine. Now, what can we talk about it? Okay. Say, let me try to explain you a bit more for here. 1 second. Okay. So now this one is something else. Okay. So this is a different one. Okay. I should kind of make a mark. So here dl of uv, you are allowed to use paths with intermediate vertices v1 to vl. So what does it mean? Here is the graph G. Okay, so I have u v. I want to consider those paths and say these are the v1 to vl paths. Okay, so say these are v1 to vl are all of them. Okay, and say that this is the shortest path between v1 to vl. That uses, I mean, doesn't use all of them. It can leave some of them, but it doesn't use anything other than that. So at this point, you can think of that there are some edges, vertices over here, which are higher than 1. So VL plus 1 and VL plus 2 and so on until something else, the VL. Now, so this is the shortest path that uses VL UV, right? Now, what is DL plus 1 UV? Now, DL plus 1 UV is basically that there are two things that you can do. You can come up with a path that anyways, so now you are allowed to use all these vertices and this. So one thing that you can do is that, okay, I don't care. VL plus 1, I don't need. So whatever I have is good enough. That is a possibility. Or you can say that, okay, since I've got that extra one, maybe using this set of edges, can I somehow reach VL plus 1? And now from VL plus 1, can I reach to V? See, here it gets split into two parts. One is this one and one is this part. And maybe this part is shorter. So either you use VL plus 1 or don't, right? So this is therefore nothing but minimum over two things, just two things. Which one? D of L UV, the set of all paths which doesn't use VL plus 1. Okay. And sorry. And among the paths that uses VL plus 1, so I am looking at VL U VL plus 1 plus DL U, sorry, VL plus 1 VL plus 1, the final vertex, right? And that's it. So there can be only two kind of paths. You have suddenly managed to got one extra bit of information, or you have got a bit of a leeway, right? A single tool, basically. VL plus 1 is a new step. You can either not use it, in which case this should give me the enough answer, or I use it. In that case, I better go through it. I go from U to VL plus 1 and VL plus 1 to V. And note that this path is a shorter path, right? I mean, one of those two. So once I define this thing in this way, again, a very simple concept. If you think about it, understanding this correctness is not a hard job at all. Okay, but the main idea is, how did someone come up with this idea? And just this. Now, see, this is a minimum over just 2 points, not minimum over in the previous one. It's not a minimum over all possible B's, W's in V. It's minimum over just two things. So it's a constant step. So, right? And once you have that, we can now do the algorithm. And I don't want to go over this whole thing right now, but now this D1, D0 is something different. Of course, they start with the kind of base cases, not base case, sorry. So what is the D0? So D0 therefore is the set of all paths, minimum path that doesn't use any intermediate vertices. So it doesn't use any intermediate vertices, meaning the only possibility is going directly. And so this is basically all the set of edge weights. Now next one is, okay, among the set of all edges that uses only one. Okay, does it anyone help? Actually not. You will realize that it doesn't help. Okay, set of all the ones that uses only two. Again, if you see that with 2, I can now go to 1 to 3 basically, right? So 1 to 3, which is now I cannot reach. Instead of that, right, I could have gone from I to 2, sorry, from 1 to 2, which is 11, and from 2 to 3, which is 4, which should be 15. So this should kind of go down to 50. And the next one, you can do that. And if you do it carefully, you realize that you will be able to have the whole thing. So I don't want to go over this whole thing line by line. You guys can, I mean, I will be, of course, sharing these slides as well as this video with you. You can go over it. And the main idea is that, okay, I have to go over all the D1 to D7 steps. But when I do that, I am done, right? Because D7 or Dn is basically you use all the vertices. Writing the pseudocode is again trivial, right? All you do is that you go from I equals to 1 to V, and now look at all the possible, every time for all the V, you look at all the pairs and you update the pairs by looking at the previous one. Now, what is the time complexity? See, here again. For everyone, so I have D6. From here to get D7, I have to update all the V square possible points. But to update any one point, I have to look at only two things and find a minimum of those two. So it's just a constant. So from going from one square to the other, this to this is just V square steps, right? And I do it for V times. So total time complexity becomes V cube. Now this is almost magical, right? And I know that this is magical, and I can only say is that I will of course upload this video, upload the slides, and you go back and think. Right? Proof of correctness is actually very easy to follow. Okay. Proving the time complexity is also very easy to follow. What is the most difficult thing here was something that has been told to us is the definition of DLUV. How you are defining this kind of concept is the key to dynamic programming. Once you define it correctly, you can go to the next step easily. So this is basically called the Floyd-Warshall algorithm, and this uses order V square V cube steps, and it can also be used to detect cycles. So if I use all of them, then for single shortest path, we have Dijkstra's algorithm and Belmont-Ford for V square and V cube algorithm. Dijkstra for only positive and Belmont-Ford for negative weights also. We have all pair shortest path of positive weights and for the for Dijkstra's algorithm V cube, but we can also get the same thing for negative weights using Floyd-Warshall algorithm. And you can see this kind of improvement slowly happening one after another. Now, again, as I told you earlier, the goal of you is not to kind of memorize Belmont-Ford, Floyd-Warshall, and so on and so forth. Okay, that is not the goal of this course. I am not going to ask you up in any place, mid-sem, end-sem, whatever, something that, oh, give me the Belmont-Ford algorithm or write down the Floyd-Warshall algorithm or something. No, I'm not even going to ask you to prove the correctness of Belmont-Ford algorithm or prove the correctness of Floyd-Warshall algorithm. No, I will be asking questions that will test your understanding. And the most important understanding for this class and anything that will, and the thing that will follow in the next week, is that for dynamic programming, how you break up the problem into smaller subproblems is the key. That is something that you can only gain by practice and practice basically, and your creativity in general. None of them are hard. Beautifully is there is a very elegant way of defining a new concept, and then it kind of automatically recurs. Okay. By the way, all of this thing that we kind of told can be modified to obtain the shortest path problem, shortest path also, not just the length. This is something that I'm not going to go into it. Okay. So was it understandable? I mean, is there some serious confusion about whatever was done? Hello?
Is it understandable?
It is understandable, correct? I mean, it is nothing to be not understand, okay? Just the main trick is in that definition. You just look at the definition and feel, wow, who came up with this definition? And okay, so then once you define the definition, and then everything kind of follows beautifully. So I think, as I told you, today's class will be slightly short, so I will stop in another 2-3 minutes. please go over this particular slides and talk. There will be tutorial this Saturday and Sunday, and sorry, Saturday and Monday. There will be a problem set on dynamic programming that will be uploaded. Okay, dynamic programming is something that we not only use in graph algorithms, but we also use in other algorithms, many other algorithms in fact, and that is what we will be doing in the next class. Okay, in the next class, that is what we will be doing. Also, if you look at the web page, so there was a tentative kind of schedule of the course that was going on. Of course, we were not following that track very well, but I have now updated that track, so you can see how, which direction the algorithm, this course will be going for the next 6 weeks. I think there are 6 weeks of classes after this before the end sem. Once again, please go over this thing. Don't try to memorize those algorithms. Don't try to understand. I mean, of course, try to understand the proof of correctness and all of that. But more importantly, try to understand or to think what went on in the mind of the person who found it, who defined that BL, UV, and so on and so forth in that. How did they manage to do that? Once you can identify that thing in your head, you will do a very good job of algorithms in general. Okay. So any questions? Any questions? Okay, good. So if there is no question, so let me stop the class now today. And please go over the slide videos. Please go over the slides. And we will be talking about more of dynamic programming in the next class. Okay, bye.
Thank you, sir.